All right, thank you. Welcome to our talk on practical Kubernetes security at scale. This is based on joint work between two teams in Schibsted, Developer Foundations and Product and Application Security. My name is Birgir. I'm a software engineer at Schibsted. I've been focusing on infrastructure and how development teams can effectively use cloud platforms.
And I'm Stian. I'm a security engineer. This is work I was involved with while at Schibsted, and I'm currently at Norway's Wealth Fund.
All right. Over the past few years, a lot of companies and organizations have embraced running containers. Containers provide a standard way to package your application code, configurations, and dependencies into a single unit that you can launch wherever you like. Containers are lightweight and portable, as they already contain everything that the application needs and can be run on any platform. Kubernetes is an open source platform for managing containerized workloads and services, and is widely used in the industries, with more and more organizations adopting Kubernetes as the platform of choice. Schibsted is a Nordic family of digital consumer brands with a mission to empower people in their everyday lives. We have leading brands in the Nordic market across news media, online marketplaces, and technology ventures. Many of these organizations are embracing and adopting Kubernetes. New technology brings new challenges, and how to secure our platforms as they are moved to Kubernetes is one of them. In this talk, we'll outline some of the steps we've taken to enable security measures and controls for Kubernetes configurations across different organizations within Schibsted. Organizations within Schibsted are autonomous when it comes to technology choices, which oftentimes leads to a dissimilar setup and having to come up with unique, brand-specific solutions. Schibsted has different building blocks that are shared and can be leveraged by different brands. Some examples include identity platforms, privacy services, payment services, and data and analytical capabilities. Developer tooling and infrastructure components provided centrally are similarly shared building blocks that support the software development lifecycle and product teams across different organizations. The building blocks form a foundation that organizations can leverage and build on top of. AWS is a cloud provider that's widely used in Schibsted. It provides a lot of services, which now include EKS, which is their Kubernetes offering. Despite EKS providing some things out of the box, there is still a learning curve to operating Kubernetes cluster and running workloads efficiently. Not all teams have the same resource capacity or expertise when it comes to investing time and effort in infrastructure, and therefore having the ability to leverage a shared building block can be appealing to teams, both small and large. For this reason, we've introduced Skates, which is a managed Kubernetes configuration, which comes with batteries included to create a fast track to a Kubernetes configuration and a runtime that's ready for production. So Skates is built on top of EKS and comes with integrations to existing CI/CD systems and has a lot of capabilities provided out of the box, and is a setup that is similar across the different organizations. So we are currently operating close to 100 individual clusters across multiple different organizations, with the steady growth of workloads being migrated and hosted on these clusters. So one of the challenges we are presented with is how to ensure a base level of security across clusters that we are managing for different organizations, and how we can drive improvements over time. So Kubernetes is a complex topic, and there's a steep learning curve to master it. The complexity makes it so it's possible to simplify application. The complexity makes it so it's possible to simplify applications, as Kubernetes now takes care of many of the things traditionally handled inside of applications. Kubernetes consists of several different parts. Firstly, we have the control plane, the control plane works to maintain the desired state of the cluster. It has several components. etcd is a key value store where the state of the cluster is persisted. There's a scheduler, which is in charge of scheduling pods or workloads onto worker nodes. API server is the core of the control plane and how users, external components, and parts of the cluster all communicate with each other. Lastly, we have a controller that watches the shared states of the cluster and makes changes attempting to move the current state of the cluster towards the desired state. Then we have worker nodes. Worker nodes run the applications and workloads. A pod represents a group of one or more containers running together. Each worker node can run multiple workloads, and a cluster can have multiple worker nodes or groups of worker nodes as it scales over time. Inside of a worker node, we have a couple of components. There's the kubelet, which is an agent that connects to the control plane and registers the worker node. And then we have kubeproxy, which is a network proxy that runs on each node in the cluster. It maintains networking rules for nodes, and these network rules allow communication to your pods from network sessions inside and outside of the cluster. There also need to be components to support or enable incoming and outgoing traffic to the cluster. And in a cloud environment, there are also cloud-specific components that become relevant. Additionally, further customizations can be done by installing external modules that can extend and enhance the behavior of the cluster and shape it into something that's usable for you or your organization. So in summary, there's a lot of components and parts to Kubernetes that make it possible to run applications on top of it. But Kubernetes does provide some basic security features, but it is in the hand of the cluster operator to implement robust security protocols when it comes to security and compliance enforcement. Ensuring we have security measures and controls in our platforms and in the building blocks, as I mentioned earlier, is key to being able to operate them efficiently. But where do we start to implement security in Kubernetes in a way that will not introduce hurdles that will kill the momentum that development teams have gotten from adopting the platform? So there are a lot of guides on best practices that are out there and best security practices. Those are all readily available on the internet. There's a lot of solutions from security vendors, so commercial solutions out there. There's also a lot of open source tools and solutions that are readily available. So for us, we have a lot of options, which is great, but deciding what to do and how to do it, that's the challenge. Depending on your business and compliance requirements, there may be different aspects that need to be considered, and it's not a one-size-fits-all. What we will be talking about are the steps that we have taken and the journey to improve the security posture of Kubernetes configurations in Schibsted. Cloud Native Computing Foundation maintains an overview of cloud native projects which are applicable in the Kubernetes context, which covers a lot of different topics. There are a lot of established projects out there, as well as new and up and coming, both commercial and non-commercial. So CNCF keeps track of the majority of these projects, and the landscape can serve as a guide. Exploring open source solutions to evaluate what gives us value has been our approach so far, and going by what is out there, we have a lot of options. But finding the right fit is the challenge. So our approach is repeatable security according to the NIST cybersecurity framework, Tier 3, to build as little as possible by leveraging existing tools. Since we already have clusters out there with production workloads or teams that are developing solutions that are deployed to clusters, we need to ensure that we don't disrupt that in a way that hampers them. We need to recognize that there may be different requirements in different teams and different organizations, and align the work with existing efforts in CloudSec and AppSec as they all contribute to the overall security posture. And lastly, to learn from others. There are other Kubernetes setups in Schibsted at this moment, and we try to incorporate the learnings from those into Scales. AWS defines a shared responsibility model that states that what they will be responsible for and what's left to the user to take care of. In the case of Kubernetes, a lot is left to the user, but with a shared building block like Scales, we are able to encapsulate some of the complexity that users would otherwise be exposed to. Similarly, we want to clearly define responsibilities for a central team that's operating clusters and product teams that may be running workloads on them. Therefore, broadly speaking, the operator is to be concerned with the operations and security of the cluster overall, and the users are responsible for the operations and security of their applications or workloads that are launched in the cluster. We as operators ensure guardrails are put in place that will enable the product teams and developers to do so. So this continues to empower developers that can still use the build it, you run it mindset with some additional support. So automation is key to scaling security. We use infrastructure as code to get repeatable security across all of the clusters. This enables the same hardened setup to be used, while also ensuring that the state does not drift. Furthermore, it enables gradual rollout of guardrails and security measures, and the ability to customize those per team, organizations, or even down to the cluster level. We use Checkov, which is static code analysis tools for scanning infrastructure as code files for misconfiguration that may lead to security or compliance problems. It includes predefined policies for checking for common misconfiguration issues, and it supports many different types of infrastructure as code flavors. And it allows us to evaluate our Terraform modules as well as our Terraform plans before we apply them. So Checkov can be integrated into existing CI/CD pipelines, which gives us a way to catch things before they are being deployed. And this gives us more confidence when it comes to making changes and applying them across the board where we don't compromise existing setups.
So before we get into how to secure single clusters, it's worth noting that the best isolation, like if you have different workloads that should be completely you should do it in separate clusters. So Schibsted is a collection of a lot of brands, and they already run in their own AWS accounts in a single AWS organization. And it made sense for us to also have individual clusters in those accounts. So the benefit is that we get extra isolation, but we don't get some of the benefits of having Kubernetes, the scaling part and all of that. So this is our target baseline. We say target because we are still working on it, and baseline because we expect some teams to go beyond this. For instance, there are already teams that do egress filtering as well as RASP type tooling. So we're going to focus on the Kubernetes parts here, and even though it's pretty AWS heavy, we think that there's learnings here for any Kubernetes setup. And the goal here is to get as much security as possible with each measure, while not getting in the way of the users, and also with the least amount of effort from our central teams. First off, we have securing the control plane, and here, there's complexity in operating and securing the control plane, and you can largely outsource it using EKS, as was mentioned, which is the managed Kubernetes from AWS. And basically, in terms of the control plane, you have everything you need out of the box. It's secured enough, and you don't have to do additional hardening. You might want to do IP allow listing if you're concerned about having the API exposed to the internet, but it should be safe by default. So having kind of solved the control plane, we can look at the data plane. And that's all about, or mostly centers around the pod. So like, how can you break into a pod? And once you're there, like, what else can you have access to? So the pod might be exposed as a service inside the cluster, and you might also have external traffic coming into it. Another way in for an attacker would be through the supply chain, introducing malicious code in the pod. And then, so once you're there, we as cluster operators want to make it as hard as possible to do lateral movement to other things, either via a container escape or via the network. And before getting more into that, let's first do a brief history of isolation. So you basically started out with the processes, trying to run different apps on a single operating system. And there's hardware features to back this up. The next step was to run multiple OSs on a single physical machine. And so we had VMs, and again, new hardware features were added to enable this. And then more recently, some tried to get the best of both worlds in terms of processes and VMs, and we got micro VMs. And if you look more broadly, new features tend to be separate hardware, or there's also research into new CPU instructions to improve isolation. So if you look at AWS and also the other big cloud vendors, they are built on VMs. So a lot of effort has gone into harden those. So they used to be more sort of less custom hardware. So the trend the last few years for AWS is that they have more custom hardware, which is this is a Nitro system. So the current generation of VMs you get on AWS is based on Nitro. So they also have a micro VM option, which is called Firecracker, and that's used for both serverless functions like Lambda, and you can also use it for containers. So in contrast to this, Kubernetes came out with new software features in the Linux kernel. So you still have the process model, but it's in software, and you're kind of losing out on all of the hardening and innovation that's been happening in the VM space. So that's why we need to do some extra work when we're trying to secure Kubernetes. So you can run it in micro VMs as well, but it's you lose some flexibility, and it's unclear how much security you gain by that. So Kubernetes is a leaky abstraction. These low-level kernel features I talked about are exposed to users trying to deploy to the cluster. So when you deploy your pod, you can also specify these low-level Linux things like namespaces, SE-Linux, and capabilities. And basically what it does is that it limits your application, your pod, to do an escape into the system. So if you do an escape, you can get to other pods running on the same machine, and you can also get to these control processes that are also just processes, like the kubelet and the kubeproxy. And the incentives there are misaligned because you are protecting the rest of the system from your application rather than the other way around. So if you're just doing a one-off, you might not want to do a lot of hardening to protect the rest of the system from your app. So the solution we're going for this is a combination of two things. So you have the container-optimized OS called Bottlerocket, which is a hardening of the VM. And then you can set limitations on what kind of security settings are allowed into the cluster via the admission control. So if you look at Bottlerocket, it was made for this purpose to be able to run containerized workloads more safely. It's an open source Linux-based operating system from AWS, and it is focused on avoiding persistence rather than isolating different pods from each other, but it also helps in that regard, using custom SE Linux tools. So a couple of the features, so they have minimized the amount of binaries, so if an attacker were to get some sort of foothold, having access to binaries can be useful, so they minimize that, and they also harden the binaries that are there. They use a combination of read-only file systems and ephemeral file systems to make it hard to tamper with files, and also make sure that after reboot you're in a clean state. And updates are done atomically, so that rather than mutating individual files, you get a fresh set of files that make up the whole version. So it makes it really easy to roll forward and backwards. And they also have a convenience function for improving the speed of security patching in the cluster. And like we chose Bottlerocket because it's a great combination of security and flexibility. So there's a lot of hardening, but you can still install custom security tools as well as other components from the larger Kubernetes ecosystem. So the second part to the equation is the admission controller, and it's limiting what is allowed into the cluster in terms of these low-level Linux settings. And you could make your own custom policies, going through each setting and see what should be allowed. And we actually did that exercise, and we came up pretty close to the existing Kubernetes standard called Pod Security Standard. And PSS is implemented with something called PSA, and is currently in beta in Kubernetes. And you can also use it with older Kubernetes clusters. So you can get a lot out of the box using those systems. And it's basically 3 levels. So you have your disabled, you have your baseline, which is unlikely to break your applications while also provide good security, and you have restricted. If you need more flexibility than that, you can use something like OPA Gatekeeper. So OPA Gatekeeper allows you to make more other types of policies as well, including limiting what registries images can be pulled from, and also verifying signatures. We actually implemented both PSA and OPA Gatekeeper, and OPA Gatekeeper is both harder to integrate and harder to use. So if PSS is good enough for you, that's where you should start. To further drive this home that Bottlerocket and PSS is a good match, we have this list of recommendations from the GitHub page of Bottlerocket. So the first column you have the recommendations, and the second you have the priority, and in the third you have our does PSS cover this or not? And as you can see, PSS covers a lot, and it's a great fit with Bottlerocket. So for instance, you can look at the second one here about privilege escalation, and that's restricted in PSS baseline. So it's a couple of the things. For instance, you have a setting called privilege, like true false. That's blocked by this, and you also have these various Linux capabilities that can be dangerous that are also blocked.
While container images are a convenient way to package and distribute applications, they may include many attack surfaces. Image scanning is the process of identifying known security vulnerabilities in the packages listed in a container image. Scanning images at build time enables us to fix any vulnerabilities identified before they are deployed anywhere. There are multiple tools available out there for this purpose, one of which is called Trivi. Trivi is an open source vulnerability scanner from Aqua Security. And Trivi detects vulnerabilities of operating system and language-specific packages, as well as having the ability of scanning for hard-coded secrets like passwords, API keys, and tokens in an image. Trivy has a database of vulnerabilities which include remediation recommendations, and that's periodically updated. But not all vulnerabilities have fixes, and depending on the context of where an image is running, the vulnerabilities may not be necessarily exploitable. So we need to ensure that there is a good signal to noise ratio to make this reasonable for developers. Vulnerabilities may not have been identified at the time when an image was being built, so it's important to also consider scanning currently running images periodically. And as we have the ability of keeping track of images across our fleet of clusters, we have the ability of doing these periodic scanning of the running images, which gives us the ability of keeping track and an up-to-date overview of potential issues. The state of a Kubernetes cluster is a dynamic one. New workloads are being launched. Cluster keeps scaling up and scaling down. Worker nodes get added and removed. Users or external systems interact with the cluster. So periodically evaluating the existing Kubernetes cluster or configuration for vulnerabilities or misconfiguration can be a useful thing to do. NSA and CISA have published a comprehensive list of recommendations for strengthening the security of a Kubernetes configuration to help companies make their environments more difficult to compromise. Kubescape is a tool that can be used to determine how well a Kubernetes cluster configuration meet these best practice recommendations. When Kubescape is run, it will capture the current state of the cluster and then evaluate it against the policies that it has built in. The output can then be interpreted to see if there are any violations to the policies, and that can then feed into actions that can be taken to improve the configuration. Kubescape can be run periodically to allow us to keep evaluating the risk and compliance scores for different clusters or configurations and enable tracking that over time. It can also be run as part of CI/CD pipelines just as well to evaluate manifest or catch issues before they are actually deployed to a cluster. Additionally, we've enabled AWS Guard Duty for EKS protection, which was recently introduced by AWS. It can detect threats related to user and application activity captured in Kubernetes audit logs. The audit logs give Guard Duty the visibility needed to conduct continuous monitoring of API activity to detect any suspicious activity there. When threats are identified, Guard Duty generates security findings and sends notifications that can then be acted upon.
So identity and access management is of course important in Kubernetes as well. Like a lot of this is left to the users of the clusters to have like minimized privileges. But it's also important to integrate properly with your surrounding environment, which is our case is AWS, and it's possible to map AWS roles to Kubernetes roles, so you have access to the control plane. And you can also go the other way around, where you give pods access to the roles in AWS so that they can use the other services as normal. So we don't talk about secret management, for instance, specifically in this talk, but once you have this, you can also, of course, use the AWS Secret Manager in that way. So this way that you actually get access to the AWS credentials from a pod, it's called IRSA. It's somewhat new, so you used to use a third-party component, but now AWS supports it themselves. And of course, IMDS v2 is also always a good thing to enforce when you have VMs in AWS. So for cluster networking policies, since Kubernetes implements its own networking, you don't necessarily have those controls out of the box. So in AWS, they have some support for like security groups with Kubernetes, but it has some limitations. So we've gone with a custom implementation called Cilium. And Cilium makes it easy to have a coarse-grained restriction on your network. So basically, there's this concept of namespaces that isolate resources in Kubernetes. So both from a RBAC perspective and here when using Cilium at the network perspective. So it's very easy to do this coarse-grain isolation. Another thing to note is that default in Kubernetes, you have this Linux capability called CapNet Raw, which allows spoofing attacks. So depending on the network you happen to use with Kubernetes, that attack might be possible to do, but in the case of EKS, that's not possible. And sort of for completeness, let's talk about the Ingress controller as well. So Kubernetes support a range of Ingress controllers by default. We happen to use ALB, which is supported. So that's the application load balancer from AWS. With that, we also get the benefits of web application firewall, as well as DDoS protection. We also make sure that all new applications that are being deployed are IP allow listed to avoid accidentally putting things on the internet. And of course, you could put any kind of security control in front of the Kubernetes cluster, and then you might want to use something like the Nginx Ingress controller to proxy the traffic to the cluster. So that was a run through of the security measures we have opted for in our target baseline. And we think this is a great combination or trade-off between security and flexibility. And while it's very AWS heavy, we think that it's applicable also in other scenarios. Like the approach, you can use the same.
Yep. And for Schibsted teams that have adopted Kubernetes, the experience has been a positive one. Everything from increased developer productivity, increased scalability and fault tolerance for services, to creating a migration path to the cloud. So with shared building blocks like skates, security controls, and guardrails can be introduced and simultaneously deployed across multiple organizations. The security measures added further empower developers and product teams that can rely on guardrails to catch misconfigurations or vulnerabilities that may get introduced in the development process. Through opt-in enforcement of security controls, team can gradually enable those as they adopt the controls.
And if you want to go beyond what we're going through here, we can recommend the EKS Best Practices Guide from AWS, as well as the Kubernetes Hardening Guide from NSA and CISA. Those go more into detail and are great resources. And of course, you can also explore the wider Kubernetes ecosystem to find the solutions to your problems. And with that, we are happy to take questions.
Thanks, guys. That was a lot. I will go with a quick question to grease the wheels before we turn it over to the audience. It's a common thing that many of us have faced, whether in our own orgs or as consultants when working with clients who are doing migration and looking to take advantage of cloud technologies, AWS, what have you, Kubernetes in the cloud. And they maybe think that, well, just by switching to AWS has more security than we do, so we're automatically going to be secure by moving to the cloud. But then you look at many additional security features that need to be turned on, configured, paid for. how many of these things we're talking about. You mentioned some tools are open source. In terms of an org that's maybe in the cloud using some of these technologies today, how much of the security stuff would add an additional cost versus just having to be turned on within an existing subscription?
Want to take that?
Okay. So given that we have gone for a lot of open source solutions here, they don't, most of these things don't add cost. So some of them do have a commercial offering as well. And of course, there's some convenience you get with the commercial offering. But you can largely trade off like doing more like the integration part yourself and keeping the cost down.
Okay. Guard duty, is that an extra cost?
That is extra cost, even if you have guard duty enabled.
Questions from the audience? Kubernetes people, AWS, curious? Anybody? All right. Oh,
I do have a question.
okay.
I have a loud voice, you don't
Shout it out.
Yeah. Have you tried running this secured workload on any other cloud environment to see how well it works security-wise? You said it's not too AWS-centric, but, well...
So this is very AWS-centric, but we think the approach is similar. So you also have a container-optimized OS in Google, for instance. And so some of the same capabilities you can get also in all the public clouds. And of course, the Kubernetes-specific tools that are open source, those would be the same in any kind of setting.
Doing this project, follow-up question, short one. Doing this project, how much time did you spend researching the CNCF landscape to kind of find mature security projects to use? Because I guess that's a full-time job.
Yes, so we mostly focused on those that are well established, and we sort of, when it looks like there's going to be a good solution down the road, maybe the best approach is just to wait. But yeah, it's definitely a lot to try to keep track of everything.
And the point here is also that it's a baseline and something that we want to continuously evolve. So essentially, it's a starting point, but it's security is something that you need to be constantly attending to.
Any other questions from the audience? Yes. That's the spirit. All right, coming over.
Thank you. Good presentation. I took in that you talked a lot about preventative security controls within an IKEA or a Kubernetes environment. Can you elaborate a bit into the more reactive parts of security when it comes to Kubernetes? Things about observability, monitoring, detection, and response in such an environment?
Yeah. So yeah, we did kind of gloss over that. I didn't mention RASP. So there are several commercial security tools that are sort of focused on this scenario you're talking about, to monitor and have actions on what's happening in the cluster. And of course, we talked about sort of the audit logs and exporting those, and that Guard Duty is analyzing some of it, but of course you can also have all the SIM solutions looking at the logs, trying to detect stuff. And like related, you also get into the CSPM space for more sort of general cloud protection and auto remediation. So there's related stuff that you could utilize. That's not only for Kubernetes as well.
I think our approach was also to build it up. You need to walk before you run. So sort of introducing some of these bits gradually, and then of course there are teams where runtime protection is a key component that needs to be added as well.
All right, last question here.
Yes, I was just wondering, you mentioned you have 100 clusters, and I guess that number will probably increase when you want to isolate things more and more. Do you have an efficient way of managing all these clusters? Do you have a platform for managing clusters? Or?
Yeah, so we are basing that around using Terraform infrastructure as code, and then we have built some automation around being able to apply that across different accounts, and then applying updates automatically. But that's things that we have sort of been building on the side to support this type of setup.